Thanks again for having me. I'm glad here today to talk about our recent research on system algorithm co-design for efficient TinyML. I'm Jilin from MIT. So firstly, I will briefly give an overview about the scope of this talk. So in this talk, we will cover some of our recent research. Firstly, the MCUNet series from V1 for tiny image recognition to V2 that allows for higher resolutions for more vision applications like object detection, exaggerate, and to V3 from inference to training. So all of these three works span across both system and algorithm. So that's why we call it system algorithm co-design. And I will try to give a shorter introduction on the first two of the work and give a more detailed introduction on the latest V3 work. And finally, I will give a little bit time about what is the connection between those tiny machine learning models and systems to the large language model nowadays, which are quite popular and as you can see, like ChatGPT models. If you have any questions, feel free to bring it up during my talk. So we'll first start with the introduction to the MCU network, which enables TinyML inference on microcontrollers. So deep learning has been going smaller and smaller and towards more applicable way in the past few years. So originally, people have been developing models like ResNets for cloud AIs based on powerful GPUs and TPUs in the cloud. And people later have been able to make the models much smaller to enable mobile AI. Example models like mobile nets that can run efficiently on smartphones. I think nowadays all of the smartphones are running some kind of neural networks locally. But can we make the model even smaller? So we think we are able to further squeeze the model size down to enable tiny AI, which enable edge intelligence on IoT devices and all kind of microcontrollers. So we hope our work MCUNet can provide a feasible solution for this kind of scenarios. So if we can squeeze down the deep learning to be tiny, there are a lot of the advantages. The first advantage is that there are already billions of IoT devices around the world based on microcontrollers. So if we can provide a feasible AI solution to enable intelligence to everywhere of your life. And secondly, this kind of hardware, they are low cost in the nature, which means that more people can afford such kind of devices, which will help democratize AI applications. And finally, these hardware and models are quite low power, which enable green AI and reduce carbon emission. So for example, such kind of microcontrollers can sometimes run based on a button battery for months without charging. It also makes deployment much easier compared to those require wired power source. And it also enables just various applications if we can deploy AI models on this kind of small hardware. However, TinyML is also quite challenging, mainly due to the memory size issues. So for cloud AIs and mobile AIs, the memory size is usually not that a big problem unless you are doing some large language models. But for most of the vision models, if you have several gigabytes of memory, that's more than enough. But for microcontrollers, the memory size is quite restricted. A typical commercial microcontroller usually only have hundreds of kilobytes of memory. So it's like more than 10,000 times smaller compared to smartphones and 100,000 times smaller compared to GPUs. So this kind of memory limitation makes the deployment really hard. And actually nowadays, most of the model designs for cloud and mobile convolutional neural nets cannot fit TinyML hardware. So here is an example. You compare ResNet 50 and MobileNet V2 and compare their peak memory required for inference compared to the hardware threshold, like here, 320 kilobytes of constraints. So even if you quantize the model into int8, there's still a 5-time gap. So you cannot simply deploy those off-the-shelf models into this kind of TinyML hardware. So this is the reason why people have been only able to do some like toy applications like recognizing like this kind of 3 fruits on microcontrollers. So we hope our work can bridge the gap and enable real-life applications like ImageNet-scale vision applications on this microcontroller hardwares. Yeah, so here I will give a rather short introduction on the MCU network. So in short, is a work that brings both the system side and the algorithm side to provide a better solution compared to simply design each component separately. So existing work can be roughly split into two categories. The first category is basically we are given a library and a hardware. Here by library, we mean the software stack that required to run the models like TensorFlow or PyTorch. So basically we are giving a off-the-shelf library and then we optimize the neural architecture itself. So it can be manual optimization like mobile nets. Those are designed by manual. Those are manually designed. And it can also be some kind of automated methods like neural architecture search. So here, short for NAS or NAS, is basically an automated way to search a neural network to optimize its accuracy or efficiency. And on the other side, there's another line of work that tunes the deep learning library given a neural network model. So for example, like TVM, so basically you are provided with a model and you don't want to change the model, but instead you're optimizing the kernels to run the models so that you can improve the inference efficiency. But we find that for TinyML scenarios, if you just optimize either of the dimension, it's not enough to provide a good enough solution for this kind of really memory constrained hardware. So MCUNet will consist of two parts. One is TinyNAS, which provides an efficient neural architecture, and the other part is TinyEngine, which provides an efficient compiler and runtime. So we need to co-design both components in the same loop to achieve the best performance. I will first start by introducing TinyNAS and show what is different compared to conventional neural architecture search algorithms. So conventional neural architecture search algorithms are basically, you can think of as a hyperparameter optimization process that you find a good neural architectures in a manually designed search space. So for example, in a search space, you have a bunch of models that consist of different depths or channel width or kernel sizes. So basically you are optimizing, you are perform hyperparameter optimization to find a good neural network according to the memory and storage constraints. The most widely used goal is to just maximize the accuracy on a certain task, like ImageNet, for example. But the problem is that for microcontrollers, the hardware is really the resource is really limited. So if you want to get a good performance for neural architecture search, you first need to design a good search space, which requires a lot of the manual tuning. And there's no prior expertise in the TinyML scenarios, which makes it even more challenging. So we propose TinyNAS, which is a two-stage neural architecture search method, which first automatically finds an optimized search space, which means that we are first provide a super large search space, then we shrink down the search space size that fits the hardware according to the memory and storage constraints. And then we perform the actual neural architecture search in this optimized search space. So how do we find the optimized search space? We use a simple heuristic that maximize the computation, which here we measure by flops, given the same peak memory constraint. So basically, this kind of hardware are really constrained in memory. So we want to squeeze in more computation within the same memory budget. And we also know that the computation of the model usually is positively correlated with the accuracy, but it provides a much more efficient proxy. So that's the such kind of heuristic we use to find a better search space. And after we find a search space, we will perform the actual neural architecture search in this sub-search space to find a good model that maximizes the accuracy at the memory constraint. That's a really just a quick introduction about TinyNAS. I had a lot of details just to give an overall introduction. And then only optimizing the neural architecture, the model itself is not enough because for TinyML hardware like IoT devices and microcontrollers, those are usually bare metal devices, which means that there's no operating systems to help you to serve the model, and there's no Python environment. There's no like deployment tool chains like PyTorch, TensorFlow, TensorFlow Lite, or TensorRT, something like that. And even if you want to use PyTorch, which requires a lot of the supporting libraries, which will easily exceed the memory limit for the tiny hardware. So we want to also develop an efficient inference library for and just a software stack to run the inference. So I will cover only a part of the techniques we use when we develop TinyEngine. The first is a general compilation-based techniques. So existing libraries like TensorFlow Micro from Google and CMSISM from ARM. So they usually use an interpreter-based method, which means that they just burn the model file to the device and also store all the binaries required to run all kinds of operators, like all the supported operators into library. And during inference, the interpreter you try to parse the model and select the required operators or binaries to run those certain operators. Yeah, but we find that it brings a lot of the overhead. So instead we separate the compilation time and the runtime. So during compilation time, we only pick out the specialized operators that are required by the model to run inference, and only compile the specific binaries to the device. So such kind of compilation-based method is quite effective, which cuts the memory usage by nearly half. So apart from those general optimization techniques, like compilation techniques, they just work for all the models. We also have a lot of the operator-specific optimizations. So here we give a example or a simple case study on how we optimize the depthwise separable convolutions. So our the models we use in this work are MobileNet-alike models. So if you are familiar with those MobileNet V2-alike architecture, they consist of a so-called inverted bottlenecks, which consists of a pointwise convolution followed by a stepwise convolution and a pointwise convolution. So for pointwise convolution, it's just a 1-by-1 convolution, and for depthwise convolution, it's usually a spatial convolution, like 3-by-3 or 5-by-5. But they don't have the interchannel interactions. So basically, applies a filter to a channel just inside the channel, but there's no in-channel multiplied by out-channel association. So it's a very efficient design in terms of computation trade-off, but there's a problem with such kind of inverted bottleneck, because we know if we want, because as shown here, for after in the depthwise convolution part, the numbers of channels are 6 times larger compared to the input and the output. This is why we call it an inverted bottleneck, because the intermediate is actually larger. So to run a convolution, we need to store both the input activation and the output activation in the memory. So if the convolution layer has n channels, then the memory required is actually 2n. So as you can see here, because for the intermediate depthwise convolution, the channel size, the number of channels is larger compared to input and output by 6 times. So if you want to perform such type of convolution, it will give you like 12 times of the memory requirement. So essentially, this kind of design becomes the memory bottleneck of the whole network. But luckily, we find that we don't really need to hold entire input and output activation in the memory, because for depthwise channel, as we mentioned before, there's no cross-channel dependencies. So after we can finish the computation of one channel, we can actually just write back the results into a buffer. So let's say after you finish the computation of the first channel, we put it in a temporary buffer. And when you compute the result of the second channel, we can just write it back to the first channels. So we call such kind of techniques depthwise convolution, which in-place depthwise convolution, which due to the in-place nature, reduce the memory requirement from 2n to n+1, which is a nearly twice cut down. So with this kind of technique, we can further reduce the peak memory saving compared to the baseline to 3.4 times. Yeah, just pass me any time if you find there's anything unclear. Yeah, so there's also other techniques like that both improves the memory efficiency and also the computation efficiency. So there's some like classic system optimization that I'm going to skip, but basically we can outperform the baseline by more than 3 times in terms of memory reduction and almost twice in terms of computation efficiency. And we also compare with all kinds of solutions from industry like TFLite Micro from Google and Micro TVN, and also CMSIN from ARM. So basically, on a bunch of benchmarks, our method performs the best. Sorry.
Yeah, just 1 second.
Is there any technical issues? Oh, okay, yeah. I will continue, but there seems to be an echo here. Oh, okay, cool. Yeah, so basically, we put everything together, and I think there previously an aberration study, but I forgot to put it here. But basically, if you just optimize the system side and algorithm side, that's not going to give you the best performance. But if we optimize everything in the same loop, basically we perform neural architecture search with the tiny engines feedback in the loop, we are able to get the best performance. And here's to show that we can achieve ImageNet level image applications on commercial microcontrollers. So we can feed different microcontrollers of different memory constraints. And we are the first time to achieve a 70% ImageNet top 1 accuracy on commercial microcontrollers, which is we think is a milestone accuracy, just like ResNet on cloud and MobileNet V2 on smartphones. So compared to the baseline, like MobileNet V2 scaled down version with ARM's currently best inference framework from the industry, we are able to improve the performance by 17% accuracy in terms of accuracy on the same hardware. So we also run some kind of like more TinyML-like applications like visual wake words. So basically, it just try to figure out whether there's a person in front of the camera or not. So we are able to achieve the higher accuracy at 3 times faster inference speed and 4 times smaller peak memory compared to the previous best results. So here is actually a very simple demo that we make. So here is just a small microcontroller, and if flash green, it means there's no person. If flash red, it means there's a person. So it's a simple demo to see what you can achieve with those TinyML applications. So as you can see, this kind of recognition is actually quite robust. So it's really helpful because as an always-on application, the camera can know when there's a person in front of the camera or not. So if there's a person, it can enable later larger, heavier deep learning models, like for example, like face identification or something like that you don't want to run it all the time because it's so expensive. But for those TinyML workloads, it can actually run all the time on your background. It's just like the audio trick words on your iPhones. And so after we done this MCUNet V1 work, we think we already get really pretty good results on image classifications, and we actually also do some like audio applications, like audio keywords. But well, we don't include a demo here, but it also works quite well because you can transform the audios into a spectrum. Then you can just apply the same CNN to it. But we later think, can we do better? Like, can we enable more advanced applications like detection or something like that? But it turns out that for the current solution, it's hard to scale to detection because the input image resolution is so limited. So we can only barely just classify the input image, but we cannot see clearly. So can we make it work even better? So we spent some time to further profile the peak memory usage of MobileNet V2-alike models. So recap that for the memory usage, it's actually dynamic, which means that it's different for different layers. So all we care about is the peak memory usage here, because if we want to fit a model under a certain hardware budget, we want to make sure that the peak memory, which means the layers with the highest memory consumption, can fit within the limited hardware resource. So here we take a look at the SRAM usage of each block in MobileNet V2 architecture. So here we can see a really clear pattern that there are several certain blocks in the initial of the neural network that consumes of the larger memory compared to the most of the layers in the later of the network. So actually, there's an 8 times gap if you compare the first 5 blocks and the remaining 13 blocks. So actually, most of the blocks that contributes to most of the computation are the later stage of the network, but they actually can already fit within 256 kilobytes memory constraint of microcontrollers. It's just the first stage cannot fit. So if we can find a way to reduce the peak memory usage by the first stage, we are able to reduce the overall peak memory by more than 8 times, which is a really big improvement. So yeah, so we find this issue and we want to find out whether we can reduce the.
So we have a question. There'll be a little bit of echo.
Okay. There might be like, yeah, I think there might be 2 questions.
On the previous slide, what exactly do the blocks at the bottom represent?
Yeah, so that's a good question. Yeah, so by block, it means that like, yeah, maybe I can draw something here. So you know that for a convolution layers that consists of convolution layers. So let's see, a typical, for example, ResNet architecture look like this. It's basically a stack of convolution layers. Let's say each square is a convolution layer. Then it has some kind of residual connections, something like this, that wraps maybe multiple convolution layers inside, maybe 2 or maybe 3. So we call this thing a layer. It's a convolution layer, and for this, for the thing that wrapped in a convolution, a residual connection, we call it a block. So basically, it's a combination of several layers. So you can do the similar analysis for all the layers, but it's just easier to visualize if you group it by blocks. So it reduces the numbers of units. So it's easier to visualize. Does it make sense to you?
Yes, thanks. Yes, thanks. Yes.
Okay, cool. Oh yeah, so I think I will continue. Yeah, just feel free to stop me anytime if you have any questions. I hope to make this as clear as possible. Yeah. So yeah, so we know that some of the initial blocks, they consumes a lot of high memory peak memory usage. So can we reduce the peak memory usage just by this kind of blocks? So we know that for normally when we want to run a neural network for inference, we are running it based on layer by layer manner. So here are 2 layers. So this is conv1, this is conv2. And for conv2, because oh yeah, I just forgot to mention. So this kind of pattern is actually quite general, because if you think of the convolution neural network design, if you have designed some about by yourself, you notice that as the model goes on, the resolution, like the spatial resolution, is getting small due to the spatial pooling. So usually after each stage, like the resolution, the height and width will reduce by twice, which means that the numbers of pixels or in the feature map are reduced by 4 times. But for most of the time, the number of channels will increase only by twice, or even smaller at each time. So essentially, the feature map size is getting smaller. So this is quite universal in all kinds of CNN designs, but not limited to mobile nets alike models. So we know that as the CNN models are getting, the feature maps are getting smaller in the later stage, just as shown here. So the conv2's output are much smaller due to the pooling or the stripe. So for layer by layer inference, as we mentioned before, for normal convolutions, you want to hold both the input activation and output activation in the memory. So for the first block, for the first convolution, if you hold both input and output, which are 2 big activations in the memory, is going to be the bottleneck, just like we showed in the last slides that the first several blocks are consuming a lot of the memories. But instead, if you just split the spatial dimension into multiple patches, here we call it per patch inference. That way, for each time, we just compute a small patch of the feature maps. Then we, but across these 2 convolution layers, so we compute only a small patch of the spatial area for multiple convolutions until we reach a certain layer. For example, that layer's output activation is really small. Then we write the temporal results into the output area. So right now, for each time, we only need to hold a small patch of the activation in the memory, which effectively cuts down the peak memory you used that requires to run those kind of layers. So we apply it to mobile NVIDIA 2 to see how it works. So what we do is basically we replace the first step of 5 blocks inference pattern from per layer inference, like here, per layer inference, to per patch inference. So because for the later layers, their peak memory is already small, so we still use the per layer inference, but we only replace the first 5 blocks with per patch inference. So after this kind of simple schedule change, we are able to reduce the peak memory by more than 8 times. So like here, the dashed block is the original peak memory by per layer inference, and after we switch to per patch inference, the peak memory reduced from here to here. So the peak memory of the whole network is no longer the 3rd block, but it now translates to here. Here is the new peak memory, which is 8 times smaller. Yeah, so we also we just did a simple benchmark. We applied such kind of simple technique to all kinds of memory network designs and provide the peak memory change. And we find that if we use a 2x2 patches, basically it's split into 9 patches, we can reduce the memory by 3 times roughly. But if we use a final grain patch size, like using a smaller patch each time, like 3x3, 9 patches in total, we're able to reduce the peak memory by 4 to 6 times across all kinds of model architectures. But we also need to notice that yes, please.
Yeah, so question is, so you're assuming like a sequential processing. What if you had some parallel processing elements over here?
Sorry, what kind of processing?
I was just saying, if you're for the patches, you're processing them sequentially, right? But what if you had some parallel processing capability? Would the same approach extend to that?
Yeah, so sorry, I don't quite get what operation capacity. Can you give some detailed examples, like what kind of operators you are talking about? Parallel, right? Parallel. Oh, okay, yeah. Oh, yeah, that's a good question. So right now, all the models we talk about, in terms of the convolutions, is sequential. So the most parallel thing we have is just residual connection layers. But we do notice that there are some other model architecture designs, for example, GoogleNet, they have a parallel architecture like this. But one thing in the recent research of efficient neural network is that people gradually finds out that the sequential model architecture have the better power efficiency compared to the multi-branch model design. So in the scope of this work, we focus on sequential processing like this. But for a parallel network designs, we think it will still work, because if you only compute a small patch, for example, if you only compute a small spatial patch each time, like this one. You just apply it to all the convolutions in the multiple branches. So notice that if you have multiple branches, you need to hold the intermediate activations, like intermediate result, for example, is output for all the branches. So it's actually not quite memory efficient, but our method can still improve the baseline. But if you want to focus on efficiency, generally, I would not recommend you to use some kind of multi-branch model architecture designs, just because it holds more memory, temporary buffers in the memory, which is not efficient. Yeah, I hope that addresses your question. Yeah. So I will just carry on. So yeah, so it seems that the patch-based method is quite effective in terms of reducing the peak memory. But actually, there's a
excuse me, another question. How is the
please.
patch related to the filter size?
Oh yeah, that's a good question. So by filter size, I assume we are talking about kernel size of the convolution neural networks. So there's actually no direct relationship except for the thing I'm going to talk about next. So
okay,
yeah, maybe I can talk about it after I bring to the next slides. Okay. So there's one issue is that this kind of patch-based method doesn't come at no cost. So essentially, if you think of the two-layer example here for the output activation, if you split it by 2x2 patches, then for each of the patch, due to the receptive field of the convolution layers, it comes from either from a kernel size or like filter size. For example, a 3x3 filter, it will give you a larger like receptive field compared to 1x1, and 5x5 will give you an even larger receptive field. So and another thing comes from the spatial pooling. So if you map the relationship from this kind of yellow block to the input of the previous convolutions, you will notice there's actually an overlap due to the receptive field. There's a spatial overlapping. So if you want to ensure that the output of such kind of inference pattern is mathematically equivalent, you need to, when you cut out the previous input activation, you need to make sure that there's some kind of spatial overlapping. But if you compute it patch by patch, essentially there's some repeated computation in just this kind of dash areas, because you want due to the spatial overlapping. And as you mentioned before, if the kernel size is larger, then the receptive field is larger, which means that there's more overlapping and more computation overhead. So I don't really bring I actually skip these slides because I don't want to put too much details here. But the general rule is that we don't want to get so many repeated computation, because computation efficiency is also something we care about a lot. So we actually co-design the neural architectures with neural architecture search and the patch-based inference schedule. So the general idea is that we want to design a model that has a smaller receptive field in the perpatch inference stage. So we want to reduce the receptive field in the first stage such that the overlapping is smaller and the computation overhead is smaller. And we want to expand the receptive field of the later stage, because here we are running per layer inference. There's no overlap from there's no overhead from the receptive field overlap issues. So, but overall, we want to keep the overall receptive field roughly the same compared to original model, such that it has the same performance on some kind of benchmarks like object detection, which heavily relies on a large receptive field. I'm sorry, but I skip a lot of these slides that due to the time issues, but that gives you a general idea of what we try to co-design here. We want to make sure that we want to reduce the computation overhead and want to maximize the network accuracy so that while still we can enjoy from the perpatch-based inference benefit. So here are some results. So compared to the MCUNet results we showed in the last section, so here is the green light. We can actually further push the frontier by a lot. We are able to achieve higher accuracy at 4 times more peak memory. So actually on this kind of visual weak-word data set, we are actually able to fit over 90% accuracy for only under 32 kilograms of peak memory, which is a really small memory size, like smaller than 32 kilobytes. Sorry, not kilograms, kilobytes. So for background on this benchmark, so it's included in a benchmark suite called like TinyML perf tiny or TinyML perf. So on that kind of benchmark, the acceptable accuracy for this data set is 80% top one accuracy. So as you can see, 90% is already quite usable, because in this data set, there's a lot of images containing super small persons. It's adapted from COCO. So we don't actually need to recognize so much small person because it's still far away from the camera. So 90% accuracy is really usable at this point, but we are able to do it in only 32 kilobytes of memory. Yeah, so we think it's a further breakthrough compared to the MCUNet V1 work. So what's even better is that we are able to actually to enable some like more fancy or complex vision applications that object detections, but not just image recognition or classification. One thing special about object detection is that resolution size is more important for detection, because you need to figure out how many objects are in the image and where are they. In compared to classification, we will just give you an overall like signal to the entire input image. So here we show the performance of a VO detection, which is measured on VOC dataset and also ImageNet top one accuracy. As we reduce image size, the ImageNet accuracy degrades but slowly, but for detection, it degrades sharply. So one good thing about our method is that we are able to reduce the peak memory of the first several layers, which means that we can now hold a much larger input resolution to enable object detection. So in terms of object detection, MCUNet based models are able to like outperform the baseline by 20%, in terms of MAP under 320 bytes of kilobytes of memory, while the V2 version further pushes the accuracy improvement by double digits by 17%. Yeah, here are just some like simple demos we make for the detection. So on the left-hand side is the face detection and mask detection. So whether if you're wearing a mask, it's green, but if you are not wearing a mask, it's showing red. So it's a demo we made 2 years ago during the pandemic. So it's kind of that day's topic, but maybe not right now. And there's also some like multi-person detection demo here. It's not super clear, but as you can see here, it's a small person sitting on the back, and our model can detect it. And there's 2 persons walking by and still detect it, but everything happens just on this small hardware that is smaller than an airport case. And actually, this is a development board, so we need to include the screen. But if you remove the screen, it's even smaller hardware running totally on a small battery pack. Yeah, cool. So finally, yeah, I think maybe we spend much more time on inference. Yeah, I think than I expect, but I think I would also like to give a more detailed talk about the training side. So in the previous 2 sections, we have already talked about all kinds of techniques we use to enable TinyML inference. But can we do better? Can we actually perform on-device training under those limited memory constraints? So why we need to learn on the edge? Because for edge AI applications, there's a lot of the user and new and sensitive data coming in, for example, from healthcare or just your biometric data like voice signals or something like that. So if we can update the model on device, it enjoys better privacy because you don't need to upload the data to the cloud. You also it also gives you the ability to customize the model and perform lifelong learning. For example, you want your voice assistants to adapt to your accent or voice. But the problem is that the training is more expensive. It's much more expensive than inference. So it's hard to fit edge devices. So here is a comparison of the memory footprint compared to training and inference. Because for training, you also need to save the intermediate activation for back-propagation. So the memory requirement is an order of magnitude larger than inference. So this is if you look at the current solution for a training, model training is usually designed for cloud like TensorFlow and PyTorch. So it requires at least several hundred megabytes to even perform to run this framework. And the best edge device we find is like MNM from Alibaba. So it also requires 40 megabytes of memory. So there's a large gap if you want to fit it on TinyML or microcontrollers IoT hardware. But in this talk, we would like to bring some like extra techniques that reduce the peak memory requirements step by step by more than 1,000 times compared to PyTorch, so that we can actually fit this kind of tight memory constraints. So the work consists roughly 3 techniques. So the first 2 are more the algorithm side. The first one is quantization-aware scaling, like to see how we can perform model update if the model is already quantized. And the second is sparse update, like we don't want to update the full model because it's too expensive, but how we can choose the best sparse update scheme. And finally, we also adapt our previous Tiny engine to support the training functionality. So let's first talk about quantization-aware training. So all the models we talk about in the MCUNet V1 and V2 work, they are already quantized, which means that we are using int8 precisions to represent the weights and activations inside of FP32. This is because int8 precisions, it gives you almost no accuracy degradation, but it saves the memory by 4 times. So it's quite popular and like almost an industry standard if you want to deploy a CNN model. Yeah, there are 2 kinds of quantization graphs. One is called fake quantization, where everything is simulated in FP32 for quantization-aware training, but this is not what we are looking for. What we're looking for is real quantization graph, where like tensors are in int8 or int8 or int32 formats, but mostly for most of the tensors that consume a large memory, like weights and activation, is int8. So int8, so for the graph on the left-hand side, it doesn't give you efficiency improvement. It just helps you to do to fine-tune a model that is better for quantization. But what we target is really on the right. It's just a model we use for inference, or we use it for on-device training. But the problem of training on such kind of quantized graph is that it's really difficult to optimize. Oh, sorry, there's a typo here. It's hard to optimize. So basically, there are several issues that make it different to optimize. The first thing is that the tensors are already quantized into lower bit precisions, like int8. So if you want to perform gradient updates, it's really hard. And there's also no normalization layers like batch norm, because for the deploying models, it's already fused into the convolution layers. So there's no normalization layers to stabilize the training. So actually, if you just perform SGD optimization over such kind of graph, compared to FP32, if you degrade for the transfer learning accuracy, it would be 10% worse on average on 10 data sets. So it's actually quite a large drop, because for this kind of data sets, the downstream data sets are usually easier. So 10% drop is like huge. So why is the quantized graph hard to optimize? So we try to figure out what's the problem between the optimization, and we find here we plot the magnitude ratio between the weight and its corresponding gradients. So here the blue line is the FP32 case, and the green line is the int8 case. And we find that in terms of the scale of the weights and its corresponding gradients, they really doesn't match in the quantized case and compared to the floating point case. So there's a huge gap because the y-axis is actually log scale. So the scale mismatch is actually quite huge. So and the pattern is different. So if you can see for the quantized models, there's a zigzag pattern, and for the floating point model, there's also a zigzag pattern, but they are not in the same period, which means that the ratio are not different for each layer. So you cannot just scale the learning rate. Yeah, please. Sorry, yeah, I think there's a question.
About 2 slides back, but what exactly is fake quantization?
Oh yeah, so fake quantization is a concept. Yeah, that's a good question. That's not a concept we need to use in this talk, but I think it's good to understand. So sometimes people want to quantize the model, and sometimes if you quantize the model, the performance will be worse compared to the floating point counterpart, because the weight and the activations they are in lower precision, while during the model's pre-training time is in FP32. So the quantization leads to accuracy drop. But sometimes people want to find to get a model that still get a good accuracy after quantization. So that's where people do quantization-aware training. So what they do is they still are training the model in FP32, but during the inference time, they will first perform a fake quantization operator. Here we show these are the fake quantization operator before using the weights and input for quantization. By fake quantization, it means that, so here is an x in floating point. Let's say its range is maybe -6 to 6. It's just a random number I provide here. So the fake quantization will first project it into int A range, like -127 to 127, and then you just perform a rounding to make it into integer levels. Basically, it discretizes this kind of tensors, and then it projects back to the original range. So compare the input to the output. They are still falling in the same range, but the difference is that the output is now discretized. And here we use a technique called STE. Basically, we know that the rounding operation is not differentiable, but here we use the approximation. Basically, for the forward time, you just discretize the tensor, and for the backward time, you just let the gradient flow back. Basically, for backward time, treat it as an identical mapping. So the good advantage of such kind of method is that during the forward time, you're actually simulating the quantization process, because after this fake quantization operator, the weight and the activation, they're discretized into 256 levels, just like the quantized intake quantized part. But you can still get a gradient update back to the weights. So after such kind of quantization-aware training, you can just convert the trained weights into int A. So you get a same performance as the training, as the quantization-aware training phase, where you use the floating point to simulate the quantization the situation. Yeah, but basically, this is just a technique to simulate the quantization during training, so that you can get a model that you are confident you still get a desired performance after real quantization. Yeah, I'm not sure if that explained it clearly. Yeah, but basically.
Thank you.
Okay, thanks. Yeah, sure, no problem. So basically, this process, they will simulate the quantization. So it's actually mathematically equivalent during the forward, but it allows you to update the model weights. But everything is in FP32, so this is not what we are actually looking for, because it's still designed for cloud, and there's no actually saving from this training. So what we do is we want to optimize a really quantized model. So let's continue. So as we mentioned, there's a difference in terms of the weight and gradient magnitude. So why there's a difference? So there's a simple derivation. I think I'm going to skip. So if you are interested, you can maybe find the slides later to see. So basically, we find that there's a systematic offset compared to the weight and gradient ratios for all the tensors. So so this is why we propose something called quantization-aware scaling. So basically, we're scaling back the gradients so that we can maintain a similar weight and gradient magnitude ratio, even for the quantized graph case. So here just a similar scale, a very simple scaling equation that is deterministically designed. So there's no hyperparameter tuning. And here the yellow line shows the int8 with scaling. So it basically matches the FP32 case. It's not identical matching, but it's good enough, as we'll show later. So basically adding our QAS technique, like here, we can dramatically improve the convergence. So now it actually matches the original FP32 tuning performance, and even slightly better. We also try other optimization techniques like LAS, which is an adaptive learning rate schedule method.
Question.
Yes, please.
Hi, G. On the previous line, could you really quickly explain what a tensor gradient is?
Oh yeah, so the tensor gradients. Yeah, I think maybe you're asking about what is the ratio, what is the value we show here, like what is this curve representing about. So this is actually so for the during the backpropagation, each tensor, which here just means weight. So the weight of each convolution layer, they will get a gradient. So here we are actually plotting the magnitude of the weight tensor itself compared to the magnitude of its gradient, which is G. So here this graph is just the ratio between W and G. So we just show that for the int A case, the ratio is distorted, like it's not really close to the pattern of IP32. So we propose this simple technique called QAS to fix this kind of ratio problem so that we can still optimize the model well. Does it make things clear for you?
Yeah.
I would have another question. When we consider the fake quantization, shouldn't we have the same problem of this zigzagging ratio? And if not, can you give me the intuition why?
Yeah, that's a good question. So in the fake quantization process, there's not going to be such an issue. There are several factors. The first factor is that if you look into the quantization process, like the real quantization process, what it does is that for weight, it's originally floating point numbers, but what we do is we extract a scaling factor out from the weight, so that this is a mathematical identical transformation. So you are extracting a scaling factor out from the weight. So let's say original weight range is like -1 to 1, something like that. But after this kind of transform, the weight divided by the scaling ratio, we want to map it to -1.7 to 1.7. So this is the int range. So afterwards, we will quantize this part into W bar, which is in int A format. So the problem of the gradient scale mismatch is just mainly due to the scaling ratio problem and the chain rule. So if you have such kind of scaling factor and the chain rule, then the gradient and weight magnitude ratio will be offset by the square of this scaling ratio. So that is the problem why we have this kind of distortions. So let's see why quantization-aware training doesn't have this kind of problem. So we'll roll back the slides here. As you can see, for the QAT process, the fixed quantization process, the input range, the input of this operator here, the range is, let's say, a floating point range, something like, so it may not be -6, maybe just -1 to 1, but it's just an illustration. So the input and output range are the same due to the QAT design. So there's no scaling factor issue here. And another problem is that they have the batch normalization operators here, which will help you to stabilize the norm of the gradients. So if you just plug in the batch normalization, I think it will also work. It's just that the batch normalization are not really designed for edge devices because you cannot get a large batch during training. Yeah, so that's the reason we think why QAT doesn't have such kind of problems. Yeah, hope it makes sense.
Yeah, it makes sense. Thank you.
Yeah, so it's a really good question. So basically, we fixed the scaling ratio issue, and now we get a good performance. So naturally, people may be wonder. So there's also some other optimizers like add-on that also just do adaptively learning rate scaling for each tensor, even each element. So how does it work here? So first thing we want to notice is that for add-on optimizers actually requires more memory because you get a two second order momentum, and usually you need to store it in IP32. So you cannot just store it in int A because it will just give you a very bad performance. So it's actually, if you consider the precision as well, it's not actually 3 times, it's actually 12 times or maybe 10 times. So compared to int A, so the memory efficiency is not really good. But even if we don't compare the memory efficiency, our method actually gets a better performance compared to add-on. So here is just some like learning rate curve here that shows that our method can bring better convergence, like the green compared to the blue, which is expected because we are getting better accuracy here. So our first technique addressed the problem that we cannot optimize the model that is quantized. But let's say now we can optimize the model. Can we just doing end-to-end backpropagation? We find it's hard because it requires a lot of memory. But luckily, as we show that even in human, like when people get to study their neuron their neuron connection update is actually quite sparse. So which means that we're not updating all the neurons all the time. We're actually only optimizing a part of them. So we actually do the same things for neural network training. So here is a graph, is a deep neural network we showed. They're consisting a lot of the blocks or layers, as I showed before. So if we want to update the entire model, it's really expensive due to the two factors. The first thing is that I need to save all the intermediate activations for the gradient computation, which is quite expensive. And secondly, if you are targeting for microcontrollers, the weights are stored in flash, which is read only. So if you update the weights, you need to save an updated copy, which is even more expensive. And there's a popular method people use for transfer learning or learning on the edge, is that you just fix the backbone, and we also only fine-tune the classifier here. So there's no need to backpropagate to previous layers. But the problem is that the accuracy is usually low if you only fine-tune the last layer, especially when there's a domain shift compared to the pre-training to the downstream task. Let's say the pre-training data sets are collected under a bright environment, and in your house, some area there's really low in the brightness. So this kind of shift may break the feature extractor. So we want to also update some of the layers. There's also another technique called bias-only update, which means that we don't update the weights of the layer, but we also only update the gradients. So if you dive into the backpropagation equation here, if you want to get the gradients of the weights, you need not only the gradients of the outputs, but also the input activation, which is what we cache for training. But if you just want to get the gradients of the bias, you don't really need to cache the input activation. So it helps you to save memory by a lot. So with bias-only update, there's no need to store the activation, which saves the performance, and we can even backpropagate to the very first layer without any saving of intermediate activation. But the problem is that if you only update the bias, the memory limitation is quite so you're not going to get the best performance because the degree of freedom is limited. So in this work, we propose something called sparse layer and sparse tensor update. So by sparse layer update, it means that we only update part of the layers. For example, we only update the second half of the layers. So we don't need to backpropagate to the very first layer. So the backpropagation will stop here, which saves the memory a lot. So we no longer need to do the entire full backpropagation, and we don't need to store the intermediate activation for the previous layers. And even for the later half of the network that we update, we can also skip some of the layers so that we don't need to store its corresponding input activation. And for some layers, we can actually only update part of their channels because some layers are so large, even updating an entire layer is too expensive. So we only update part of the channels. So here, basically, we are providing a very flexible design space for backpropagation. So you can flexibly update only part of the network layer parameters to support transfer learning. But the problem is how we can pick the best updating schemes. So so this is just a summary from all the things we discussed above. But how we can find the layers, what layers to update that contributes to accuracy better. So our basic idea is we are performing some kind of sensitivity analysis. So that we just pick out the layers that are more sensitive or they contribute more to the transfer learning performance by analyzing its contribution to the transfer learning. So what we do is we just fine-tune each layer in a network on a specific downstream data set to measure the accuracy improvement. So here are some data points on either CNN models or transformer models. So you just update each of the convolution layers and measure the delta accuracy it has on the downstream data sets. So here is the x-axis is the layer index, y-axis is the accuracy improvement. So let's first look at the convolution layer case on the left. We find that there's a clear zigzag pattern, and we find that there are two observations. Firstly, the later layers are more important. As you can see, the delta accuracy generally goes higher as the model gets deeper, which is also reasonable because the model is we have a higher level of feature abstraction in the later of the network, so it's more helpful. And the second thing we find that inside each of the mobile net block, the first pointwise convolution in each block contributes more, which corresponds to the peak in the peak points in the graph. And for the crest points, it corresponds to the later 2 layers. So we don't want to update them because they provide minimum contribution. And also it's actually more expensive because the input feature map is larger. Yeah, but that's some kind of details. But basically we can also perform the same analysis for different kind of models. For BERT models, something might be different. Instead, the middle layers are more important instead of like convolution layers that like the importance is getting larger as the model getting deeper and deeper. And one thing we notice is that even though we perform such kind of analysis on a certain downstream task, it actually generalizes quite well to different other data sets. So we just need to do this kind of analysis once, and we can apply it to all kind of the downstream tasks we are care about. So we don't need to do this like on the device, like after deployment. We can do this beforehand on a cloud GPU to analyze importance and just use it as a fixed scheme. So it's more applicable to IoT, all kind of downstream data sets. So there are also some details. We not only include the layer level importance analysis, we also just to study how many layers we want to update the bias, and how many, like we also perform an analysis on what if we only update part of the channels in the layer, like we only update 1/8 of the channels instead of all the channels. But basically we get this kind of contribution curves, and we can perform simple optimization, which is we assume the contribution can be additive. So which means if you update 2 layers, we assume the contribution can be summed up. So what we want to do is run simple optimization to maximize the overall contribution sum. But we don't want to exceed the memory constraint. So we want to still stay behind the memory constraint while we maximize the contribution, like sums of all the layers or all the parameters we update. Yeah, so this is just a heuristic or a proxy, but we find it work pretty well. So here is a case study of what really update plan may look like. So on the upper hand is on the upper side is the memory usage of each block in a MobileNet V2 network. So the blue one comes from the activation cost, and the yellow one comes from the wait cost. As you can see, the activation cost is getting lower and lower, just as we showed in the previous section, the MCUNet V2 section, where the initial layers, they are having a really large activation. While for the later stage of the network, because the channel dimension gets larger and the weight size is really just related to the channel dimensions, so the weight on the later half of the network is large. So we notice that because updating bias is only related to the activation, so we can actually only update later half of the network, so we can skip the saving of the initial half of the activations, which are large. And for the weight, we are mostly updating the because we only back propagate through here, so we cannot update the weight in the earlier half of the network. But we can only update the weights in the intermediate stage of the network, because it has both low activation memory and weight memory. So here, the intermediate stage of network is basically a sweet point. So we update some of the layers in the intermediate stage, but we still find that the later stage of the models are more important in terms of accuracy, as we profiled before. So our search scheme will also update some of the layers, but sparsely, like only part of the channels to save the memory. So this is a really reasonable and readable, but it's actually discovered automatically by our previous search criteria. Yeah, so we perform such kind of sparse update scheme optimization for a bunch of models on all kinds of baseline models, so we can outperform the baseline. So our update scheme can reduce the peak memory usage by 4 to 8 times, while still getting higher transfer learning accuracy. Yeah, so finally, like although we have all this kind of good algorithm solutions, we want to make it runnable on those edge hardware. So we need to extend our previous inference-only engine to support training. But due to the time limitation, I think we will just briefly go over this section. So Yeah, so like just similarly, the runtime is heavy and memory is heavy. Want to optimize this stack, so we are still using a compilation-based method, but at this time we are no longer only writing the inference graph. We also burn in the backward graph here, but it's still a compilation-based mechanism, and we perform some kind of reordering to reduce the memory footprint. So basically, we know that there are a lot of operators in the training graph, like inference and back-propagation, like gradient calculation, and also the update nodes. So if we reorder some of the nodes, we can significantly cut down the memory usage. So yeah, I don't think we have time to go into every detail, but there's some kind of the system optimization we can make to further bring down the memory cost. And so put everything together compared to the naive baseline like TF-Line model with full update, we are able to get more than like 20 times reduction in terms of the memory and speed improvement with our solution. But actually TensorFlow Lite, they don't really support training. So this is just our own baseline we are making here. So I mean, compared to the real training baseline by PyTorch, the magnitude of improvement is even larger. Yeah, and also our tiny training engine is not restricted to IoT devices or microcontrollers. It can also just scale to all kinds of edge devices like smartphone SoCs, Jetson Nanos, and even Raspberry Pis. So here is a simple demo that we do on-device training. So here is a microcontroller development board. So here we burn a ImageNet pre-trained model with a random head to do visual wig words. We just feed the image through the camera on the screen, so it's easier to make a demo. So as you can see, this is the original randomly initialized model. So when it asks to detect a person or not, the results are basically quite random. So here's a zebra, it just recognizes a person. So we change the image as the random initialized model. As you can see, the performance doesn't really make any sense. So the accuracy is roughly like 50%, it's just a random guess. But now we can perform some kind of on-device training on this memory board. So the label signal for the ease of development, we're passing through the serial port. So basically, we're feeding the image through the camera and we perform and we get a label from the serial port. So there's some like quick training. So afterwards, after the training, as you can see, the recognition is quite precise, whether there's a person or not. Yeah, so like better still, this kind of the trained model can transfer to real time. So here is my colleague, so it can well recognize whether it's a person or not. So actually, we are just doing this kind of on-device learning demo, everything just running on this microcontroller within 300 kilobytes of memory, and we can perform downstream transfer learning. So finally, I would like to also spend a little bit time about like how we can move forward to enable efficient large language models. In the right now, I think it's definitely one of the most popular topic nowadays. So as you can see, as the model gets larger, so nowadays the language model based on transformers, they're getting larger and larger. So y-axis is actually the log scale. So they are getting to several hundreds of billion of parameters. But the problem is that the GPU memory is also growing, but at a slower speed. So as you can see, nowadays the largest GPU is like 80 gigabytes, while the models are already over 500 billion parameters, which is more than 1,000 gigabytes. So GPU is already a specialized hardware for AI, but it's still not enough. We need efficient algorithms to bridge the gap between the model size increase and the slower hardware capacity increase. So as we showed before, in terms of memory, the most advanced H100 GPU has only 80 gigabytes, while GP3 already uses 350 gigabytes. So even for the cloud case, like the GPUs, they are still short in memory, just like the microcontrollers for smaller models. Nowadays, the large language model is just in a very similar scenario where the model size is much larger than the hardware resource. So we still need memory efficient techniques to help here, similar to TinyML. And this is actually quite essential because even for super big companies like Microsoft, they are running out of their server resource. As we can see just in a few days ago, the ChatGPT Plus upgrade is passed because the OpenAI is running out of enough cloud compute to support the inference of this kind of large language models. So we really need to reduce the cost of serving these models. So one very promising method to reduce the cost of models, as we discussed a lot in the previous slides, is just to do the quantization. So if we can do wait A-bit and activation A-bit, we short for WA8 quantization, we can reduce the cost compared to FT16 by at least twice. But it has been widely adopted as an industry standard for convolutional neural network. But why not large language model? Why people have not been using it for large language models? So one issue is that as the model gets larger, typically around about 6 billion parameters. So here, the upper line is the FP16 performance, and the lower line is the quantized performance. As the model gets larger to a certain point, there's some systematic outliers emerge in the activation. So these outliers are so large. So if you quantize activation using int8, there will be some precision loss. So the model performance will degrade to almost zero, like here, it just degrade to zero. So the problem is that we cannot just apply WA8 quantization like CNN models. And there's one method that called LRM-int8, which is very interesting because it performs mixed precision decomposition to the activation. Basically use FP16 to represent outliers to preserve the accuracy. So that is the only method that can preserve the accuracy here. But the problem is that such kind of mixed precision method is not efficient in terms of hardware. So if we compare the latency compared to FP16, the LRM-int8 method is usually always slower. So we don't really want to slow down the inference. So the current quantization method is either inaccurate, like it degrades accuracy, or it's slow. So we want to bridge the gap here. That is our latest work called smooth quant. So you actually migrate the quantization difficulty from, so you actually address the problem by a simple observation is that, so let's see on the left-hand side, there's an illustrative figure that the activation is hard to quantize due to the outlier here. When we find the weight, it's actually easy to quantize. So it's actually quite flat. So the real statics are on the right-hand side. So this is the activation originally, as showing, here is the channel dimension. As you can see, there are some really large values, like this is actually 70. The axis is not continuous. So the red values are much larger compared to the rest of most of the values. So these are outliers. And in terms of the weight, it's actually quite flat. As you can see, there's no significant outliers here. But one good thing is that these outliers are quite consistent, which means that if one channel has some outliers, it has outlier for all the examples. So for the token dimension, it's just this dimension, which means that we can actually perform a linear transform that multiply a small value to the outlier channels. And then we multiply the inverse of the value to the corresponding weight channels. So this is a static transformation. But after the transform, it will smooth out outliers like here. It will also make the weight slightly harder to quantize, like as shown on the left side, but they are still fairly easy to quantize. So after the transformation, everything can be quantized A-bit. But due to the time constraint, I will skip the details here. But the conclusion is that our model is basically more accurate. It's just both accurate and efficient. So we apply it to all kinds of public models. We can match the accuracy of the FP16 performance, and we can also improve the efficiency. So for the OPT 1.75 billion model here, we can reduce the number of GPU required to serve the model from 8 GPUs to 4 GPUs, while still getting slightly faster inference speed. So essentially, it reduced the cost of serving by twice, and you are still getting a faster inference. And we also scaled the model up to apply it to a proprietary model from NVIDIA, which is more than 500 billion model size. And for the first time, we are able to run this kind of model within a single node due to the GPU memory saving from the quantization scheme. And we also advanced recently there are some popular open source model called Llama. So it's from Meta and it's quite popular in the open source community. And the Llama model has introduced something called switch G-rule activation function, which is really hard to quantize for the activation. But our method can still address such kind of scenarios, and we can still almost preserve the accuracy when we apply quantization. Yeah, so that's a really quick deviation to the large language model side, but I just want to show that the TinyML concept is relative. So it basically means that the hardware is smaller than the model, so it's tiny, so it's hard. But for the even for other scale of models like large language models and GPUs, it still will face the similar problem because the model is always growing faster than hardware. So that is why we want to. Our technique should be general, and we should be looking forward to also to the large language model side. So finally, our method has been like the MCUNet series work have been getting some media coverage from, for example, this is the MIT news. We get it to homepage twice, and we also get cover from MIT Tech Review, Wired, Engadget, and some other media coverage. And finally, our models, our repos are all open source, both for the MCUNet repo and also for the Tiny Engine repo. So you're welcome to try it out. And finally, yes, it's just this is a very old lab photo 3 years ago. Yeah, I just want to thank you for listening to the talk. Yeah, that's all the contents here. Thanks.
Yeah, thank you so much, G. Some questions.
Yeah, please.
Yes, one second.
Thanks so much for taking the time out this morning to speak with us, G. I was curious about your search space optimization of MCUNet techniques. You mentioned these two parameters, these two hyperparameters, your width multiplier and then your input resolution of the search space.
Yeah,
I was curious about what your thought process was going into tuning these hyperparameters. Specifically, you will experience trade-offs in model size and model accuracy based on how you change width multiplier and input resolution.
Yeah, that's a good question. So yeah, so actually this kind of two-stage, there are different hyperparameters we optimize over the two-stage. For the space stage, we are optimizing the input resolution and the overall width multiplier. And for the neural architecture stage, we are optimizing the very micro architectures, like the kernel size for each layer, like the expansion ratio for the inverted bottleneck block, and how many layers, how many blocks in each stage, something like that. But how we pick the subspace, or how we pick the input resolution with multiplier for this stage is based on flops heuristics. Because of course, the best thing you can do is you just sample each of the search space and you perform neural architecture search and see what's the best accuracy you can get for each kind of resolution with multiplier combination. But it's not really realistic because it's too expensive. So based on heuristic that if the models inside that search space that meet the memory constraints have larger computation or flops, which it usually means that it gets a better accuracy. So all we do is for each of the space, we just randomly and uniformly sample maybe 10,000 or 1,000 of the neural architectures, and we just profile the memory usage of each model, and we only preserve those models that meet the memory requirements. And then we measure the average computation, or we plot the CDF of the computation of each the legal models inside each search space. And we just use the search space that have the higher average computation. So notice here's no search involved. It's just random sample to ensure that we are getting an unbiased estimation of each search space. Yeah, I hope it makes sense.
Thank you.
Yeah, actually, one thing interesting is that in the MCUNet V2 work, we are no longer using this kind of two-stage search space. Basically, after we get a better super network training technique, we are actually putting everything into the super network. So in our MCUNet V2 work, we get a super network that supports both the all those micro level architectures and also the input resolution and also the width multiplier difference. So previously, we need to separate this is that at that time, the neural architecture search algorithms are still not mature enough to support, for example, like width multiplier. So people need to manually design one. But later, as the technique gets better, we just put everything into a search space and do a joint search.
Thank you. I also had a quick question. I know that for these large language learning models, one of the major constraints is that as these models continue to grow,
Yes.
the amount of memory that they use continues to grow at a much greater rate than than how much memory GPUs have grows.
Yes.
And
Yes.
so I was curious as to whether you think that there will ever be a time, either based on like the optimizations of these language learning models or based on the advancements in GPU technology, where it would be possible to run a really advanced language learning model, like a pre-trained version of that locally on either a smartphone or like a personal computer.
Yeah, I think that's a good question. So currently, I'm actually optimistic toward that trend. So there are several reasons. So the first thing is that yeah, of course, like it really depends on how good you are requiring for the large language models to be. Like if you want it to be a GPT-4 level reasoning, that is really hard. But if you just want to get a GPT 3.5 level, like personal assistant alike models, and right now people have found that even for a model that's only 7 billion parameters, like the Llama models I mentioned here, people just distill the Llama model against OpenAI. People find that even 7 billion or 13 billion models that can already perform reasonably well for a lot of the daily use cases. So for this kind of models, it's already feasible to deploy on your smartphones if you perform some advanced quantization methods. So that for that kinds of models, it's already feasible to run on your personal computer. Like it can generate maybe dozens of tokens per second. It's really already useful at this time. And in terms of those really like over 1 billion parameter models, yeah, I think we will still be able to run it on a personal computer because that the gap is actually not that big. So one issue is that people have been able to do like 4-bit or even lower bit quantization of the weights. So if you only think about the storage, like 1 billion parameters, if you run it in 4 bits, it's only like 50 gigabytes. It's not that too small, but still a reasonable size. But if you're able to quantize it into 2 bits from the algorithm optimization, it's going to be 25 gigabytes in terms of memory usage. So nowadays, personal computers, some of them are getting like 64 gigabytes of memory. So I think it's reasonable to run those things on a laptop. And in the future, as the hardware grows, I think it will be more and more affordable. So I do think there's I'm really optimistic that we're able to run over 1 billion parameter models locally in the future. But of course, there's also another issue is that the state-of-the-art models are still getting larger and larger. But for that side, I'm not sure how large they are going to grow. So if it's going to so for that part, I'm not sure. I would just, but I think for nowadays models, we will soon be able to run it on local devices.
Thank you so much. Just to quickly follow up on that, on the last part we're talking about. So how long do you think we can make the state-of-the-art models larger and better before we will just be like limited by the hardware and software optimization will no longer be like available? You just have to wait for the hardware to catch up with the software, I guess, or the size of the models.
Yeah, so for that part, I really don't have too much information because I think nowadays the state of their models is just OpenAI models. So no one is knowing what is their like roadmap look like. So how much the model is getting larger. But I think one of the but I think but personally, yeah, it might be biased for me, but personally I think it will assume that the hardware will catch up because even for OpenAI's their GPT 3.5 model is actually, I heard it's actually quite small. So it's definitely no bigger than 50 billion parameters, maybe just 10 or 20 billion alike because it's really fast and low cost. So I do think even for OpenAI, they have the incentive to compress the model down without hurting too much performance. So I do think it's not like they are just scaling up the model. They are actually also quite sensitive about the price. So if they keep that kind of design in mind, then I don't think we will like running out of the hardware resources like in the very near future. Yeah, I mean, if you can definitely scale up the model, but I think they may not be that necessary. yeah, in terms, especially if you want to commercialize it.
Yep, thank you so much. I have also a quick question. If you could go back to your when you went through like fake quantized graph versus real quantized graph. So I was a bit confused when you say that quant-aware training is the fake quantized graph. So I'm just confused at how, even though you run quant-aware training, it actually does not save memory. So does that apply to all quant-aware training, whether you're converting it to floating point 32 or whether you do quant-aware training when you convert it to int 8? Like both applications actually do not save memory?
So like I think there are multiple ways of so in the training. So if you want to analyze the memory usage for training, so it basically comes two parts. So the first part is just the model itself. So I mean, So the first part is just the model itself. So you need to store the model weights and all the parameters in the memory. Like for example, here is the weights, here's the weights. And the other part is just the input activation, because sometimes you need to calculate the gradient of the weights. You need to save the intermediate activation in the weights. So if you want to measure the memory usage for the model, the training requires, is basically just activation plus weights. So the most simple thing you can analyze is to just look at their data type. So if they are really in int 8, then you save everything in 8. But if it's in 32, then you save them in, if they're in AP32, then you save them in AP32. So it's natural that if you save them in AP32, it's going to be 4 times more expensive compared to int 8. Yeah, I'm not sure if that addresses your question.
Yes, thank you. Just one last question.
Thank you, Jilin. I have another question about the smooth quant. You mentioned that for original smooth quant, the activation function is hard to quantize because the outlier of it is not fluent enough. So you use smooth quant mQuant. Interesting. How could you give some specific mathematics that you use to smooth quant this activation function?
Yeah, that's a good question. Yeah, let me see if I have the slides here, because to keep it short, I just skipped it. Let me go through the slides to figure it out. Yeah. So so here is a like I will show like slides containing what we actually do here. So let's say here is a weight activation quantization. So let's put some notations here. So this is the channel dimension, and this is the token dimension. Token dimension means that different words are different tokens. So you can think it as a batch dimension or something like that. For the weight, this is in channel and this is out channel. So when I say outlier, it means that for activation, there are like some really large values, like something like 16. But of course, in naturally, it's much larger. It's more than 100 times larger than most of the other values. But here is just an illustration. So because we are doing a matrix multiplication, like A multiplied by B equals C, which here we are doing X dot W. So this is a linear transformation. So it's natural to see that if we apply a scaling factor like alpha here into this column, and then we multiply the inverse of alpha, like alpha1 divided by alpha into this column of the weights, then it's a mathematically equivalent transform, right? Because when you multiply it together, these two terms cancel out. But if we choose a small alpha, then we are able to suppress. For example, if we choose 0.25 here, we are able to make this minus 16 to minus 4 and minus 8 to 2, something like that. But of course, we are at the same time increase the magnitude of this row. So to be more specific, what we do is for we first perform a calibration stage, but it's offline before deploying the model. We run a bunch of calibration samples through the models, and we measure the range of the activation. For example, now this is a set of activations, and we get the absolute max of the activation, which is 21629. And we also get absolute max of the weights along the input channels. Around the output channels. So for each input channel, you get an absolute max. So because the weight and activation they are quantized both by int8, which means that we want to make the quantization difficulty roughly the same for X and W. So what we do is very simple. We just we want to make sure that we select the multiplier or scaling factor such that the maximum value of the corresponding channels are the same for X and W. So what we do is basically calculate the max X divided by max W and get a square root. So now we get a scaling factor like 1413. So for X, we divide it by the scaling factor, it's something like this. And for the weight, we multiply by the scaling factor, it's something like this. Then as you can see, after the multiplication, the maximum value of each column is the same for weight and activation. And we assume that the range of the tensor determines the quantization difficulty. Now that they have the same range, it means that they have the similar difficulties. And one good thing is that for the weights, we can, another detail is that for the weights, we can just fuse the multiplier into the weights value. But for the activation, we actually fuse the multipliers into the previous layer. For example, the previous layer before the linear might be a layer norm layer. So we can just fuse the scaling factor for the activation into the layer norm weights. So essentially, there's no change in the graph, but it's just a mathematically transformation before you apply the quantization. Yeah. Let me know if that addresses your problem.
Yeah. Thank you. Thank you so much, G. I think this was a really good summary of 4 different, top papers of yours. I think this is very helpful to show the class here to what extent you've been able to take your research. And I'll follow up with you by email then. Thank you so much.